All right, so yesterday we left off with how do you multiply and divide using scientific notation. And I don't know about you, but when you did your homework, I'm hopeful that you guys practiced using the calculator. Of course, you figured out, and I showed you how to do this manually, but really and honestly, you should just do it with the calculator. All right. So I showed you how to multiply. Let me show you how to divide. So if we had something like 4 times 10 to the 10th, and I asked you to divide that by 8 times 10 to the 5th, what I want you to think about mentally is this. What is 4 divided by 8? 1/2. What's that as a decimal? 0.5, right? So 0.5 times, these have like bases. Remember, the base is that big 10. And then you've got the exponents. What is the rule? Remember up here we have the rule for multiplying. What is the rule if we have a base to the b divided by the same base to the c? You subtract what? Subtract the exponent. So this is really a numerator exponent minus the denominator exponent. Be careful not to confuse yourself and do the denominator first for some reason. It's kind of always top down. All right, so here's our rule for subtracting exponents. If they're our rule for dividing like bases with exponents. So in this case, we would have 10 to the numerator exponent minus the denominator exponent. So we have 0.5 times 10 to the 5th. Is this in scientific notation? I'm hearing a no. No, I hear another no. Maybe you don't know. Why is it, those of you who are thinking no, why? You want to help us out, Bryce? Exactly. 0.5 is less than 1, and it has to be between 1 and 10. So let's go ahead and convert just this into scientific notation. So here, I'll do this in green. I wish the decimal was here, so I will have to move it over. And it'll just be 5 times 10 to that. I moved it 1. I have to look at the number and say, was it a little guy or a big guy? Was 0.5 a small number or a big? It's a small number. It's less than 1. Therefore, the exponent is negative. And then I'm going to bring down this 10 to the 5th. Then I can combine these two by saying 10 minus 1 plus 5. So my actual answer is 5 times 10 to the negative 1 plus 5, which is just 4. To be honest, though, what do you really want to do? 4 EE10 divided by 8 EE5 equals, and you're done. Use that calculator. Fundamentally, I want you to understand, what is the purpose of the 10 to the? What does it do? Is that really 4? 4 times 10 to the 10. Is that 4? Yeah, you want to help us out? Moves the decimal spot. Exactly. So really, scientific notation, all it is doing is moving the decimal spot and making it a heck of a lot easier for us to write large and tiny numbers. Okay, that's it. All right, so let's move on to adding and subtracting. You will do this a lot less in chemistry, but you should know how to do it. So addition and subtraction with scientific notation. You know that W slash means with, right? Okay. So what if I gave you the problem 3.0 times 10 to the third plus 5.0 times 10 to the fifth. And I asked you what that equals. In fact, this is what question 14 was on your homework last night. So here's what I do. I'm going to shift that decimal 3 places. It's a positive 3, therefore the original number or expanded form number is a big guy. So I move the decimal 1, 2, 3. This is how I do it on my homework, or if I'm working it out on a quiz or a test. So this is really just 3,000. This is 1, 2, 3, 4, 5. So I've got all of these zeros here. So it's a 5 with 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. Did I do that right? Yeah, I think so. Yep. Please don't forget the rule that your math teacher taught you about commas, because the whole point in your math teachers teaching you about commas will all of a sudden, now you're going to understand why. In chemistry, some of the numbers that we're dealing with have something along the lines of 20, 23, 24, 25 zeros. If you have a number that's like, no joke, this long on your paper and most of it is zeros, your eyeballs can't see that. So to group those zeros in threes is the whole reason you have commas. So get used to doing commas. It will become helpful for your eyeballs. All right, so I don't know about you. I learned math where you stack the numbers like this. And then you go down. There's a 3, a 0, a 5. Okay, 503,000. Are we done? No. Why? What should I do? Put the decimal. Where is the decimal?
Where should it be?
Uh-huh.
After the first 5.
Oh, you're thinking let's convert it back into scientific notation. Yeah. So good. If the problem was given in scientific notation, you should report the answer in scientific notation. And I think the directions last night on the homework did in fact explicitly tell you report the answer in scientific notation. So we wish it was right here. Where is it currently? It's at the end of the number. So we're going to say that this is 5.03, and I moved it 1, 2, 3, 4, 5 places. And I say self, should this 5 be positive or negative? The original number was a big guy, so we're going to keep it positive. And last but not least, we box our answer. It's always a good idea to box your answer. I'd like you to just notice, and maybe if you have a different pen, you could. What some people may have thought would be a good idea is I just like, Vasquez said we can combine those and combine those. So 3 plus 5 is just 8 times, that looks like a weird times, hold on. Times 10 to the, maybe I just add the 3 and the 5 there, and this could be an 8. That looks good. And I'm not going to lie, that's kind of logical. If you don't know what you're doing, it seems logical. But that doesn't work. Because remember, that 10 to the third and that 10 to the fifth is shifting the decimal of the 3 and the 5. They're not their own entity. Yesterday, when we were doing multiplication, it was so okay to do that, right? We could totally do that because of the commutative property of multiplication. And that's because the middle action or the middle operation that's happening between these two things is in fact multiplication. So it's like 4 factors being multiplied together, and who cares what order you do it in. That on today's, those are not factors, those are terms. Terms are things that we add or subtract together. So you can't do this. So if you wrote this down, do a big circle and a no thank you. That's not what we do. But it is something that I have seen. So I just wanted to show you a common mistake, because mistakes are how we learn. All right, get that calculator out. If you have only iPhone or Android, it won't work. You have to actually have a scientific calculator. And I just want to show you a calculator tip. So go ahead and in your notebooks or in your notes here, calculator tip. If you hit the second function and then it's a button that says DRG, and I only know this, unfortunately, for this calculator right here, the one that you have. I do know that the other scientific calculators do in fact do this. I just don't know the buttons. So is it DRG? Oh no, it's DEL. Sorry. Nope, DRG. Okay, yours. Ooh, I don't know. I don't know what that one is. So anyways, oh, that's yours. You are going to hit the second function in the DRG, and what should come up is something that looks like FLO, which means is expanded form. Or SCI, which is scientific notation. So if you were to put, go ahead and put the 503,000 in your calculators, everyone who has an actual calculator. And then see if you hit second degree and change it to psi, and then hit equals or enter, and it should change it to scientific notation. So here's what I want you guys to research. If you have this calculator or another calculator, even this one, it looks similar, but it's a slightly different model. So what you're going to want to research is how do you convert in your calculator, so put the model number in, how do you convert from standard form to scientific notation, and it should tell you the buttons to push. I just know it personally from that calculator because I've used it forever. I think I had one probably when I was in college. So you want to research how your calculator converts from expanded form to scientific notation. And the reason being is it makes it really nice and easy. If your answer is an expanded form, you just hit a few buttons, it puts it in scientific notation, and then you don't have to think about it. You don't have, especially when you got lots of zeros. Did you figure it out? No? So 503,000. Okay, share that with your table. But be careful, it's now scientific notation. Get clear with it. Once you've converted your calculator to be in the psi form, now put something simple like 55. And hit equals. You're like, what the heck is 5.5 times 10 to the 1? So when you have like smaller numbers, you're going to have to convert it probably back to flow. Flow is the normal way our calculator works. Okay, nice, huh? So, did you get it? Did you figure it out? Did you guys figure it out? Okay, nice. And I do know, as much as I can see, I can't figure out how to do it on the smartphone. Somebody in first period said there's probably a calculator app that might allow you to do that, so maybe you download that. So put 503,000 equals. Okay, so that's the number, right? So hit second and then the DRG right there, right next to it. And scroll over to side. Now hit equals. See, nice? Yeah, nice. Yeah. And then what's a real bummer is you're going to put this away and like come back in 2 days. And then you want to do something like 8 times 7. Do that real quick. Watch what happens. And you're like, what the heck is that? It's putting everything in scientific notation. So now go to second function. Hit DRG. Go back to flow. And now it's back to normal. Okay, nice, huh? I know, I love it. It's such a great function. On yours. Oh, so it won't convert it. Darn. Okay. No worries though, because if your calculator doesn't convert it, or if in fact, you know, you're working with your phone and you don't have some fancy app, look at me. There we go. It's fine, because look what we did right here. We knew how to convert an expanded form number into a scientific notation, right? We walked ourselves through it. It's okay. You still need to know how. For time's sake and for your eyeballs' sake, it's sometimes helpful to have your calculator do it for you. Also, when you're taking the SAT or you're taking the exam and you want to be really fast with your time, that's helpful too, to just make sure your calculator does it. All right. So, like I said to Abigail, that was my cheat sheet. I looked at your paper. Make sure you convert it back to flow. So when you do simple math, like 9 times 9 is 81, and you get some weird thing 8.1 times 10 to the 1, you're not like, what the heck's going on? So make sure it's back in flow. So to wrap up this, in a nutshell, a few rules to think about. When adding or subtracting, with scientific notation, first do 1, make it be expanded form. 2, add and subtract to get the answer, like do the normal math. Add or subtract, whatever it is it's asking you to do to get the answer. And 3, convert your answer back to scientific notation. Or just use your calculator. Again, not because I want you to be lazy, it's because I want you to be efficient. And I want you to be correct. And you're human, so the more you have to work something out, the more opportunity, not for mistakes, but what I call mathematical errors. It's not that you don't know how to do the math, it's that you made a silly error. And those happen, and then those are frustrating because then you have a wrong value and you continue to work out your problem and then the answer's wrong and you're like, why? And it's not because you didn't know what you were doing, but because maybe you missed a 0 or something. So try to use your calculator, but do understand the whole purpose of scientific notation, and that is, again, to write very large and very small numbers easier. Now, let's move on. Why else do we use scientific notation? And the answer to that is significant figures. Significant figures. So, sig figs, sometimes you'll see me, SF is sig figs, or SFS, sig figs with the S at the end. So sig figs communicate accuracy of the measuring device. So that lab station back in the corner, when you guys were analyzing or naming different pieces of equipment, you had a graduated cylinder. Remember I told you guys, oh, it's graduated, it's smart, versus the beaker. What if I wanted you to measure 25 milliliters of liquid in this, and you did, and 25 milliliters of liquid in this, and you did. You'd write 25. Both are 25. Yet this, you can be sure, is much more accurate than this. So sig figs allow us to communicate to other scientists how accurate the device is. Because 25 mils in this and 25 mils in this seem like the same thing. But they're not actually. We know for sure you're at 25 all the way down to the 10th place, or the first decimal. Like you could be 25.0. Exactly. Whereas this one, you're like, okay, I guess it's a 25-ish. And sometimes it doesn't matter if it's ish. If you're cooking, 25 mils of water, although we in this country don't do milliliters, but most countries do. Who cares if it's 27 or 28 or 20? Just throw some of the liquid in your pot and you're good, right? So cooking, it doesn't matter. But if a pharmacist was making a drug for you, it would matter. You'd want it to be exactly, very precise. If somebody's looking at your water quality, you would want to know what chemicals are in our drinking water very precisely. If you're throwing chemicals into your swimming pool, you don't have to be as precise, right? Pour a little chlorine in there, you're all good. Give or take a little bit more, a little less, whatever. Okay? So, there are reasons to be more precise and reasons to be less precise. So what we're going to do right now is I'm going to hand out this packet to you. Please don't lose it. It took me forever to photocopy. It's a lot of paper. And once you're all completed with it, it's going to be worth 100 points to you in the lab section of your grade or collaboration section of your grade, because you will be collaborating with your peers throughout this week. And collaboration is worth 15% of your grade. So don't throw away 100 points by losing this paper. I really like the quote at the very top of this. Only those who have the patience to do simple things perfectly will acquire the skill to do difficult things easily. My daughters were ballerinas, and they danced like 20 hours a week when they were in high school. It was hard. They'd leave here, bell rang at 3:20, they're jumping in the car, going to ballet. We didn't get home until 10 o'clock at night, and then they had homework to do. Hard. When they were at ballet, often they were doing the same exact bar exercise. Bars when, ballerinas are standing at the bar doing their beginning warm-ups. They would do the same exercise as maybe the 5 and 6-year-olds. Why? Well, it's because if you can do the basics perfectly, then you can do complex dances easily. If you're a musician, I was a musician. I still am. I just don't play as often. And I remember my piano teacher, every day you have to do your scales. So I'd sit there and do my scales in all of the different keys over and over and over. Why? Because then when she gave me this like Chopin piece to play, or Beethoven or Bach, it was easier. I don't want to call those music pieces easy, but you get the point. If you're an athlete, why are you still trying to do push-ups? Why do you still have to run? Because if you can run perfectly, then the game is easier. Right? About your art. Sometimes you just got to go back to paper and pencil. If you're a paper pencil artist, or if you're a watercolor artist, do those basic skills, and that's what makes you perfect. And the reason why I'm putting so much emphasis on this is, let's just face it, you guys are going to leave this class and many of you will never do chemistry again. But if you understand some of the things that we're learning here, the life skills, it's about this idea of repetition with the basics, so that way later it's easier, which is why I'm kind of honing in on scientific notation, because you're going to be using it quite a bit throughout this class. And if you're not doing it perfectly, then later those hard problems will be even harder and more difficult. If you are somebody who struggles with those multiplication tables, you're like, 7 times 6 is what? I don't remember. 7 times 6. Whoever talks about that, right? Okay, thanks for being honest. Here's what you guys, so what? You're 15, 16 years old. And you don't have them memorized like that. Like, remember when you first learned, it was like a competition in school, and yeah, who cares? Learn them now. Practice. Practice now. Although long division, don't waste your time. Just use a calculator.
Exactly.
But you also could say, well, multiplication, don't waste your time. Just use a calculator. But really, if you have to type in 6 times 7 equals on your calculator, that's going to get frustrating to you when you're doing more complex math problems and more complex chemistry problems. Try to remember those basics of math, and if you struggle with them, as you're in the shower washing your hair, you could be like, 5 times 1 is 5, 5 times 2 is 10, 5 times 3. Why not? Do it. All right, I loved that quote. It was just nice. You could read this for your enjoyment at another time. Go ahead and flip over to this page 30. So what I'm going to do is I'm going to give you an example number. You are going to tell me the number of sig figs in that number, and then you're going to tell me what rule tells you the number of significant figures in that number. So the first example is going to be 359. If you look at the very first bullet point, by the way, since this doesn't have a number, let's make that very first bullet point number 0. And it reads, non-zero integers are always significant. Non-zero integers are always significant. 3, 5, and 9 are all non-zero integers. Therefore, this has 3 sig figs. And the rule number that told us that is rule 0, because we called that bullet point 0, right? You guys caught that? Okay, let's try another one. 5.637. Hold up on your hand how many sig figs you think that is. All non-zero numbers. All non-zero. There's a 5, there's a 6, there's a 3, there's a 7. Are those all non-zero?
Yeah,
But they're not significant? How come?
because after 3,
Yeah.
the number 3 isn't significant, and it doesn't
right. Most of the time in real life, after 3 decimal places, it really doesn't matter. In chemistry, it matters. Totally matters because we're dealing with things that are very tiny, very small. So the rule says all non-zero integers count. So this is in fact 4. It does count. I like that we shared that though, because a lot of us think, like, really? The what? Tenths, hundredths, thousandths place? Who cares? It's the thousand. It's 1/1000th of something. It does matter. So all of those are significant. We're going to say 4. And rule number 0 is the rule that told us that. All right, what about if we have a number like 5032? We know that 5, 3, and 2 count, right? So there's 3 there. Rule number 0 told us that. Is there a rule to determine whether that 0 is in fact significant or not? Look at the rules under zeros may or may not be significant. Which rule? Marcos found a rule. Anyone else found a rule? Amanda found a rule. Gabe found a rule. Good. A couple of you found a rule. Marcos, what rule tells you whether it's significant or not?
Zeros between two non-zero numbers are significant.
Yep. Rule number 1. Good. So it is in fact significant. So there are 4 sig figs. So rule number 1 told us that. I like to call that a sandwich 0. So if a 0 is sandwiched between 2 significant figures, right? The 5 and the 3 are the bread, and the 0 is like the peanut butter and jelly. All right. How about 525,010? All right. Are we fair with 5, 2, 5, and 1? Those are significant because of rule number 0. We learned from the third example, this 0 is sandwiched, so therefore it is significant because of rule number 1. All right, somebody find a rule for that last 0, because it's not sandwiched. There's nothing on the right-hand side of it. So is it significant or is it not? Is it Colin, right? Colin found a rule. You want to share with us which rule? Are ambiguous. Wait, did you read rule number 2 or rule number 3? Number 2. Oh, if a number has a decimal point. Does it have a decimal point? I mean, it does, technically, it's assumed. It's at the end of the 0. Is there anything to the right of where that decimal place would be? Are they there? No. They're not invisible. They're actually not there. So rule number 2 isn't what we're talking about here. Rule number 3 reads, if a number does not contain a decimal point, like this one, zeros at the right end of the number are ambiguous. Ambiguous means, so look at this example that they gave, 3,100 miles. It could be 2, the 3 and the 1. Maybe that second 0 counts. Maybe the fourth 0 counts. You don't know. And look what they did to show. They put it in scientific notation. So this particular problem, we say is ambiguous, and you can do A and B for short. It could have 5 sig figs, and I'll put in blue. It could have 6 sig figs. We're not sure, so we call it ambiguous. If you do not know, so if you do not know, go with the smaller sig fig. Okay? So if they were like, well, pick one. Is it 5 or is it 6? You'd always go with 5. Better to be less accurate, then assume something is more accurately measured. You don't know if that was a beaker or a graduated cylinder, so assume it was a beaker. Assume the less accurate. All right, let's practice some different numbers. What about 205,000? There. 1,205,000. Oh, I forgot to put rule number 3 on this. That determined the ambiguous one. All right, so what are we thinking here? Show me either on one or two hands, your choice. Or you could even do, this is sign language, American Sign Language for A, ambiguous. So it's ambiguous, it's 1, it's 2, it's 3, it's 4, it's 5. Is it 6, 7, 8? What is it? I think it's 3. Which 3? Which numbers? Oh, do you think rule number 3?
Yeah.
Oh, rule number 3? Rule number 3 is telling us what? Those zeros that are ending the number, they're not to the right of the decimal. So this number is, in fact, ambiguous. This is significant. This is significant. That is significant because of rule number 0. The sandwich 0, yep, it's significant because of rule number 1. But we don't know about those. Therefore, it's ambiguous. And after you write ambiguous, you need to say it is either 4, 5, 6, or 7. So when we're doing practice, and you're going to be doing this a little bit later in this packet. By the way, don't do this packet at home. This is to be done in class only. I'll tell you if ever these should be done at home. For the most part, they should be done here. So when it's asking you to report how many sig figs on a number like this, you would say ambiguous 4, 5, 6, and 7. Okay? What if that same or similar number, 1.205, how am I for time? 2 minutes? 1 minute? Let me show you this one. So this number, this right here, you guys, is not a sig fig. Why? Because remember its purpose. All it does is shift the decimal place. So now we've got 1, 2, and 5. We know that from rule number 0. We know our sandwich guy from rule number 1. Oh, fix your notes. I keep forgetting to put 3, those trailing zeros. All right, what about these 2 zeros after the 5? Look at rule number 2. It says if a number has a decimal point, it does. Any zeros at the right end of the number are significant. So if it's ending the number, this is significant. It's ending the number. It's to the right of the decimal. So that's rule number 2. Now what about the 0 between the 5 and the last 0? It is sandwiched. Therefore, it too is significant. So this has 1, 2, 3, 4, 5, 6 sig figs. It's the same number in example number 5. It's just now we know for sure it's 6. Have a nice rest of your day.